So when we're thinking about quality management, we have to think about how do we monitor our quality levels over time. One of the most common ways of doing that is by using control charts. So when we think about quality control charts, we're thinking about taking samples of my product or even interviewing samples of customers and determining if the average of those samples is within an acceptable range. So in a control chart you typically would have a upper control limit, a lower control limit, and a center line or nominal line in the middle. And then each sample that you take will have a normal distribution, and you're looking for the average of that sample and whether it falls between these two control limits, the lower control limit and the upper control limit. This is an example of a good looking control chart. So in this example, we've got our lower limit and our upper limit, and all of our data is kind of in the middle. We have variability, of course, but that variability that we're seeing would be attributed to randomness, not attributed to any particular problem. However, if our control chart starts showing other features, it can indicate a systematic problem, such as like a machine breaking down or a bottleneck that has crept in, or a problem with an employee or a raw material. So when your control chart does not look like this, it gives you some insights into your process. So let me show you some other examples. This would be considered a run chart because even though we have variability, well, it's trending low. It's lower than our nominal line. And if we keep going, it's likely to go below our lower control limit, which would be a bad thing. So for any chart that looks like this, we would stop the process and try to determine the root cause of the problem, or what we would also call an assignable cause of variation. This type of chart is what we would call a sudden change. So you'll notice here at the end of the chart, you've got a big jump from the bottom all the way to the top. And this would indicate something happened between these two samples that aren't necessarily random. So we might investigate that. There's not necessarily a reason to stop the process, but we would investigate if there's something going on. And then this is a control chart where we would certainly stop the process. You've got a sample point above the upper limit and actually another point below the lower limit. And really, if you have any points outside of your control limits, you would stop the process because you have an assignable cause of variation, meaning you have an abnormality that's causing a problem in your process. So when we think about control charts, we are thinking about these, of course, in manufacturing settings. You would see control charts in any type of manufacturing equipment, would be monitoring process data. But you also see these sorts of charts in service settings. I mean, even in fast food lines, you'll see, waiting time trackers. And when the waiting time gets too long, it starts blinking red. That's a form of a control chart. So you can see them in a variety of process settings. So there's several of what I would call just the most common types of control charts. An R chart and an X chart are probably the most common. An R chart is, or also called a range chart, measures the variability of your process samples to determine whether each sample that you're taking, the variability within that sample stays within an acceptable range. Whereas an X chart, or also called a mean chart, determines whether or not your process average is staying within that acceptable range between the upper and lower limit. But you could also do quality control charts related to defects or problems. A P chart measures the proportion of defective products. You could also monitor customer complaints in a service setting using this type of chart. And a C chart measures the number of defectives within a unit to determine if that was within an acceptable level. Now, when we are thinking about quality management, quality control, control charts certainly help us look at data over time. But maybe that's not the only thing I'm interested in. I might also be interested in what level of quality is my process capable of producing at. So, when we think of quality levels, you might have heard the term Six Sigma, but you can have 1 Sigma, 2 Sigma, 3 Sigma, 4 Sigma, 5 Sigma, 6 Sigma quality, with 6 Sigma being the very highest level of quality and 1 Sigma being pretty poor quality. But how do we know exactly what level we're operating at? We can determine that through our process data, through process capability calculations. So, process capability is typically used in manufacturing settings, so there might be the occasional service setting where it works. But it's the ability for a process to meet your engineering design specifications. So you would need to know your target for your design specs and what is allowable around those specifications. So we're looking for our process to look like this, where you have a lower design spec and an upper design spec. So this process will be determined to be capable of our target level of quality. But you'll notice when we look at this other example, the normal distribution exceeds the upper specification too far. So this process is not capable because the spread is too wide. Now, I really like this graphic here because it actually shows the difference in the type of spread you would expect for different quality levels. For our highest level of quality, Six Sigma, you see this blue line, and you'll notice that the Six Sigma curve is kind of tight and skinny right next to the nominal value, which means most of your data is grouping really tightly to the target value that you want. As quality level goes down, though, the curve goes down because you have more variability and more spread in your process data. So when we are Six Sigma, we've got a lot of data really close to our target value. But when we go down to 4 Sigma, the curve is shorter and wider. And when we get down to 2 Sigma, it's even shorter and even wider, showing more variability. So the more variability that our process has, the lower the quality level. Whereas if we can reduce variability and make that curve tighter and closer to the nominal value, we will have higher levels of quality. So we can actually calculate the specific level of quality we are currently capable of using 2 major metrics. The first one is called a Process Capability Index, or CPK. And that's a measure that basically measures the 2 halves of the normal distribution, the left-hand side and the right-hand side. And it measures both variability and centering. So CPK you can actually calculate as your overall process mean minus your lower spec, your lower engineering spec, divided by 3 times standard deviation of your process. Separately, you can calculate the other side of the normal distribution, which is the upper spec minus your process mean, divided by 3 times the standard deviation. You'll get a different number here. Unless your process is perfectly centered on your target, in which case these 2 numbers would be exactly the same. But usually you're a little off center, and if you are off center, these would be different numbers, the minimum of which you would call your CPK. Now, CP is a measure of just variability or spread. And this is calculated by taking your upper engineering spec minus the lower spec, and then divided by 6 times standard deviation of your process data. So a final point is our values for CP and CPK don't exactly tell us our quality level unless we have something to compare it to. So this is a table of comparisons that will tell you your quality level. So 1 sigma, of course, being the lowest quality, 6 sigma being the highest quality. So when we look at our reference values, in order to be capable of a certain level of quality, your CP and CPK values would have to be equal to or higher than the reference. So let me give you an example. Let's say I calculate a CP and CPK equal to 1.1. Then I would say the process is capable of 3 sigma because it's over 1.0, but not yet 4 sigma because it has not yet reached 1.33. So this is simply a reference table that helps you interpret the level of quality that you're currently operating at.